Hi everyone, myself Lohit Dalal, lecturer, Electronics and Communication Engineering Department, Jain Polytechnic, Belgavi. Today I am going to discuss about Unit 3, Digital Coding of Analog Signals. Okay, in previous session I have discussed about quantization process, quantization noise, and different digital pulse code modulations or pulse modulation methods. They are PCM, pulse code modulation, and differential pulse code modulation methods. In this session I am going to discuss about delta modulation, adaptive delta modulation, comparison between pulse modulation methods, and next different line coding techniques. Okay, next digital delta modulation. Okay, so before going to this delta modulation, we just talk about pulse code modulation and differential pulse code modulation. In a pulse code modulations, what exactly we are doing means all samples are we are going to take and we are going to encode the signal. Okay, so here what happened, there is a bandwidth is not saving here. Okay, so we are utilizing the entire bandwidth of the channel. Okay, so in a differential pulse code modulation, just we are going to take the difference of the samples. Okay, so difference of the samples we are going to take, whatever the sample will come, that sample is going to be encoded. So one advantage we'll get here, we are going to save certain amount of bandwidth. Okay, if you want to improve further bandwidth of the system, so we are using the delta modulation. Okay, so in delta modulation, just we are going to encode the only, we are going to take the error signal, that error signal is going to be encoded. Okay, in a delta modulation. So error signal question arises, what is the error signal? Okay, error signal means it is a difference between the input signal and the quantized signal. Okay, input signal, we suppose we take it as a x of t, and error signal is a x e or eq of t, eq of nts, and quantized signal is x cap of nts. Okay, so here difference, how you define difference, or error, how you define error is the difference between the input signal and the quantized signal. So here step size to be defined, how it is, because how means suppose input signal is greater than the quantized signal, the step size should be plus delta. If suppose input signal is less than the quantized signal, then step size is minus delta. Okay, here input signal is defined or named with the symbol x of t, and quantized signal we are naming it as a symbol x cap of t. Okay, error signal we are naming it as a e of nts. Okay, and also in digital or delta modulation, one bit requirement is needed to the encode the data. And also in DPCM, the error signal is quantized and coded based on the quantized output. The length of the encoded bits for each symbol will differs. Okay, in order to reduce the transmitted bits, one bit quantizer is used. Okay, so let's discuss about block diagram of delta modulation transmitter. Okay, the delta modulation transmitter consists of a sampled input x of nts, and error signal you will get here e of nts, that is the difference between the quantized signal and the input signal. Okay, so here one bit quantizer is available here, and also it is similar to the differential pulse code modulation. Okay, so just here we are using the one bit quantizer. Okay, and also delay ts will be there, and also we are naming it as a prediction filter. Okay, we are going to predict the output, then we are going it to the input signal. Okay, it is simple or similar to the DPCM system. Okay, in what exactly we are doing here, e of nts means error signal you are getting, error signal you are going to encode. Okay, whatever the error will get, that error is to be encoded. This e of nts will be there, right? This e of nts is encoded. Okay, so how exactly error signal will get, it is the difference between x of nts means sampled input signal minus quantized signal. Okay, so whatever this quantized signal will get, no, this quantized signal. Okay, so we will get the difference, that is the error, that error signal is encoded and it is given to the output side. Okay, so here you will get the some steps, okay, step size. How you are getting the step size means x cap of NTS, x of NTS is greater than the quantized signal, then you will get the plus delta or a positive information will get positive, plus delta value will get. Okay, if suppose x of NTS means sample input signal is less than the x cap of NTS means sample input signal is less than the quantized signal, you will get the minus delta. Okay, so in this way you are getting the output. Okay, so this is the block diagram of the delta modulation transmitter. Okay, so plus delta means you are naming it as symbol 1 is transmitted, minus delta means symbol 0 is transmitted. Okay, so this is the block diagram of the delta modulation receiver. To get the original signal at the receiver side, the receiver signal is passed through the delay or the prediction filter, and it is followed by the low pass filter. Okay, in order to recover the original signal, we are going to pass through the low pass filter. Okay, and there are some certain advantages and disadvantages of the delta modulation system. Okay, in advantage, it transmits only 1 bit per sample, hence reduces the transmission channel bandwidth, means you are going to utilize the channel bandwidth. Okay, and also transmitter receiver implementation is simple compared to the pulse code modulation. Okay, so drawbacks of or disadvantages of the delta modulation system: poor startup response. Okay, starting response of the delta modulation system is slower. Okay, next, slope overload distortion. Slope overload distortion means that is whatever the difference between the input signal and the demodulated signal will be there is a some amount of distortion will be there, that is known as a slope overload distortion. This can be avoided. How it is means you have to vary the step size. Okay, so if you vary the step size, automatically this slope overload distortion is overcome, but in delta modulation the variation of the step size is not available. Okay, so granular noise or ideal noise. Granular noise means when the input signal is very slow varying and step size is very large, it introduces an error, is known as granular noise. Okay, so alternatively, what you have to do here, in order to avoid the granular noise, you have to vary the step size. Okay, plus delta and minus delta will be there, you have to vary, and also step size is to be decreased in order to reduce the granular noise. Okay, so next there is a concept called as a adaptive delta modulation. Okay, in order to avoid the granular noise, and the slope overload distortion, adaptive delta modulation is used. Okay, in extra one block is adding, means in order to control the step size, we are using the what? Okay, we are using this adaptive delta modulation. We are naming it as an updated version of the delta modulation. Okay, so in the performance of the delta modulation can be improved by making the step size can be varied. Okay, so by varying the step size, you can easily overcome the granular noise and the slope overload distortion. Okay, so resulting method is known as the adaptive delta modulation. So this is the block diagram of the adaptive delta modulation. Adaptive delta modulation, what is consist of? Exactly, it consists of 1 bit quantized. It is similar to the delta modulation, just one block we are going to add. Okay, at the output side you are getting the plus delta, okay, or a minus delta, some signal you will getting. Okay, so in terms of steps you are getting. Okay, in order to avoid the granular and slope overload distortion, you are using the logic for step size control. Okay, this logic means you are going to adjust the step sizes. Okay, so here x of NTS is the input signal. Again, you are similar than the delta modulation. Error E of NTS will get. Okay, that is error signal. How you are going to get the error signal? It is the difference between the sampled input signal and the whatever the will get quantized. Okay, so we'll get the error. Okay, that is depending on the sampled input signal is greater than the quantized signal, then you will get plus delta. Okay, if suppose it is less than, you will get the minus delta. Okay, so you are going to suppose there is a slope overload distortion you are getting, just you are going to adjust the delta. Okay, so adjust your step size. Okay, in suppose you are getting the granular noise, what you have to do, you have to decrease the step size. Okay, so this is the block diagram of the adaptive delta modulation receiver. Okay, so to get the original signal at the receiver, the received signal will be passed through the what? It should be passed through logic for step size signal, and also there will be a prediction filter, and finally you are going to pass through the low pass filter in order to get the original signal at the receiver side. Okay, that is known as adaptive delta modulation receiver. Okay, so you have to get the original message signal, means original input signal you have to get at the output side. So advantages of the adaptive delta modulation is slope overload and granular noise is reduced with the help of a delta modulation. Okay, in delta modulation what you are doing exactly? Okay, range of the delta modulation. So in delta modulation, just you are going to sending the, you are making the you are just you are going to encode the input signal, you are going to pass. Okay, so in adaptive delta modulation we are having an extra block to adjust the step size. Okay, in adaptive delta modulation just we are going to adjust the step size according to the frequency of the input signals. So this is the comparison between pulse code or pulse modulation methods. Okay, so here pulse modulation methods means what exactly? Pulses are modulated, means here input signal is in terms of a pulse only. Okay, so here some parameters will be there. Okay, first one, number of parameters in pulse code modulation. Here 4, 8, 16 bits are sampled. Okay, it uses only in delta modulation, it uses only one samples. In adaptive delta modulation also it uses only one bit for one sample. Okay, in differential pulse code modulation bits can be more than one, but it is less than the pulse code modulation. Okay, in differential pulse code modulation you are taking the difference, then you are going to encode the value, encode the sample. Okay, whatever the difference will get, that's difference to be encoded. Okay, so next, levels and the step size. Okay, in a pulse code modulation the number of levels depends on the number of bits and level is fixed. Okay, so in delta modulation step size is fixed and cannot be varied. Delta modulation, yeah, step size is kept constant because we don't have any extra block to vary the step size. Okay, in adaptive delta modulation we are having the step size variation block. For logic for step size control, it is going to control the step size. Okay, in order to avoid the granular noise and the slope overload distortion. Okay, and also in differential pulse code modulation also step size is fixed. Okay, so next parameter, quantization error and distortion. Quantization error depends on the number of levels used. Okay, in pulse code modulation it depends on the what? Number of errors, number of levels used. Okay, so next, in delta modulation slope overload distortion and granular noise is present. What exactly previously we discussed? Same. Okay, same slope overload distortion and granular noise present. So next, adaptive delta modulation quantization noise is present but other errors are absent. Okay, so next, in differential pulse code modulation slope overload distortion and quantization noise is present. Okay, next, transmission bandwidth. Transmission bandwidth is highest bandwidth is required since number of bits are high. Okay, in delta modulation lowest bandwidth is required. Adaptive delta modulation lowest bandwidth is required. Bandwidth required is less than the pulse code modulation. Feedback, there is no feedback in the transmitter or the receiver. Feedback exists in the transmitter. Okay, in adaptive delta modulation feedbacks are exist, and also in differential pulse code modulation feedback is exist. Okay, so in a complexity of implementation, pulse code modulation, it is a system is complex. Okay, and all three, differential delta modulation, adaptive delta modulation, differential pulse code modulation, all are simple in nature. Okay, next, line coding techniques. Okay, line coding technique means whatever the digital data will be there. Okay, that data should be okay, mapped or a displayed on a or a okay, that data should be converted into a waveforms. Okay, means you have to draw you have to convert it into a waveform suitable for transmission over the communication channel. Okay, there is a line coding technique, okay, used to map the digits or symbols into a pulse waveforms. Okay, so it is known as a line coding. Okay, in line coding there will be a two types. Return to zero means RZ format. Okay, means pulse for half duration of the time TB. Okay, non-return to zero means pulse for full duration of the time TB. Okay, the pulse occupies the full duration of time. Okay, return to zero RZ means pulse occupies the half duration of the time TB. Okay, so there will be different types of line coding techniques. First one, unipolar NRZ and unipolar NRZ, polar NRZ, bipolar code, Manchester codes. Okay, so see here, first one, unipolar NRZ format. Unipolar NRZ format means in a positive logic. Okay, if suppose symbol 1 is going to transmit, okay, symbol 1 is represented as a plus A volts and symbol 0 is represented as a no pulse is present. Okay, so advantage of this is poor timing, low frequency content, simple. Okay, long strings of ones and zeros are okay, and also one problem is that synchronization problem will be there. Synchronization between the input and output will be there. Okay, so next concept, there is a polar energy means polar non-return to zero. Okay, here it is not going to non-return to zero. Okay, here plus when in a positive logic, suppose symbol 1 is going to transmit. Okay, so 1 maps to a plus a volts. Okay, so 0 maps to a minus a volts. Okay, you are going to show in a both the ways. Okay, polar energetic format you are showing to signal into a both the sides. Okay, symbol it means so plus, so amplitude it matters here. Okay, so if suppose transmitter data is 1, okay, that is represented as plus a volts. Suppose symbol 0 is transmitted, that is represented as a minus a volts. Okay, so advantage is better average power, simple to implement. Okay, and also long strings of ones and zeros, and also there is a synchronization problem will be there, and also there is a poor timing will be there. Okay, so next concept, bipolar code. Okay, bipolar means it is bipolar means it is available in plus a volts or minus a volts. Okay, there are three signals are available, minus a, 0 and plus a volts. Okay, one, the in a positive logic, one is shown, one is maps to a plus a volts or a minus a in terms of alternation. Alternation, or alternatively we are going to represent. Okay, 0 maps for no pulse. Okay, suppose symbol consists of 1 0 1 0 0 0 will be there. Symbol 1 you are representing as a plus a volts, 0 you are representing no pulse. Again symbol is to be represented in a one alternative manner, so we are showing it as a minus a volts. Okay, so that is a bipolar code. Advantage is long strings of 0 causes the receiver to lose the synchronization. Okay, long strings of 0 means the 0 should be continuous in nature, that time it loses the synchronization, suitable for the telecommunication systems. Okay, so next concept, there is a Manchester code. In a Manchester code, how you are going to define? Okay, in previously what you are going to do here in a bipolar bipolar code, just you are going to represent the symbol 1 as a plus a volts, and also in plus symbol 1 as a plus a volts or a minus a volts in an alternative format. 0 for no pulse you are representing. Okay, in a similar way here, symbol 1 maps into a minus a by 2 first for TB by 2 time duration. Okay, in half duration of the pulse you are representing as a plus a by 2. Okay, means half duration of the pulse you are representing as a 1 as a half duration, and next what you are going to do, you are representing it as a negative minus a by 2 for a next half duration of the pulse. Okay, in a similar way 0 maps into minus a by 2 half duration of the pulse, again my a by 2 for the half duration of the pulses. Okay, so half duration of the pulses you are going to represent. Okay, so next there is the advantages, every interval has a transition in the middle, timing recovery is easy, simple to implement, suitable for satellite telemetry and optical fiber communication. Okay, thank you.